So away you go whenever you're ready, Geoff. Thanks.
All right, sounds good. Are my slides visible?
Yes.
Perfect. Right, then I'll give it a go. I'm sorry I can't be with you. My third batch of COVID, but all I've got is brain fog, so this could be quite incoherent, but we'll see how it goes. So what Stuart asked me to do was really to try and summarise something about the industrial and commercial impact of all the last 65 years of corrosion work, which, since I wasn't involved in all of it, I thought I'd just pick on something that I do know about, which is things that have been going on since the 1990s. And of course, since I've worked in the aluminium industry now for nearly 50 years, I made it very aluminium-based and very aluminium surface and science and technology-based, and very much related to microscopy of those surfaces. So it really all, this particular feature really got going back in about 1996, when some Norwegian researchers reported that the surface of aluminium sheet was characterised by micrograined surface layers, not surface layers as it says on the slide. And this was found by a student working at NTNU. And so I was asked, what did I think of that? And so I hadn't heard of it, so I asked everyone around in Alcam, where I was working at the time, and everyone said, of course, this can't possibly be true, because if it was true, we'd all know about it, because we know more about the surface science or aluminium alloys than anybody else. So that was interesting, because I thought they probably had got the Norwegians were onto something. And they also said that, the control of these surfaces was really important in controlling the surface corrosion properties of aluminium alloys. And they'd found some quite nice things about controlling filiform corrosion by looking at the properties of this layer, and particularly by cleaning it off. But they thought it formed during a high temperature anneal, not during the rolling process. So just like, although the Norwegians were first in getting to the pole, the South Pole, as you can see from the illustration behind. They claim to be first in finding deformed surface layers on the surface of aluminium. Of course, this turned out not to be the truth. In fact, they'd been found many years earlier. If you go back to almost the 1920s, they'd actually been discovered by George Beaune. And it was interesting that George Beaune came up during Stuart's talk, and there had been 2 building medals awarded to people from within UMIST. But you can see that Beaune had already decided that something happened, interestingly, on the surface of metals subjected to things like plastic flow, particularly for polishing. And the only difference he noted, he thought that the layers that formed during things like surface polishing were amorphous layers. And that's because of really the power of the microscopes he had at the time, but not enough to really establish that these were actually ultra-fine grained microstructures. But so in this case, the Norwegians hadn't discovered anything new. They'd rediscovered Beaune layers. And these Beaune layers have turned out to be really important. And so much of the work that's led to our understanding of what these layers do on aluminium and other metals has really come from all the work that's been done at UMIST. So just to summarise, we now know that whenever you hit an aluminium surface with a rolling mill, hot or cold, or whether you grind the surface or machine the surface, that you produce these ultra-fine grained deformed surface layers. And these deformed surface layers control many of the properties, particularly the reactive properties, the corrosion properties, the adhesive bond durability properties of aluminium surfaces. And these are absolutely vital role in determining the behaviour of aluminium surfaces in industrial application. They're critical in architectural applications, they're critical in automotive sheet applications, they're really important in beverage cans, they're really important in blackening of rigid food containers, and they also not only control the corrosion properties, they can control surface appearance, like the control reflectance. And it's really through control of these layers once we discovered what they were there, and we could investigate them in great detail, we could understand how to properly clean surfaces and how to properly pre-treat surfaces and how to properly coat surfaces, such that we could get much better surface experience. So this work has been absolutely critical in really determining how things work in service and in expanding markets for aluminium alloys in automotive, packaging, and architectural applications. So really critical stuff. Very soon after I heard of the work that had been done in NTNU by Hacken Leth-Olsen, I was up in UMIS talking to George Thompson, gave him a piece of 5754, in this case a building product, so it's cold rolled H16 temper. we just looked at it in the microscope. I think Shairam Zhu probably did this work. And what the absolutely critical thing that was available in UMIS was the ultramicrotomy and high-resolution microscopy. And very quickly, this is the first sample we looked at, we saw that what Hacken Leth-Olsen had seen was absolutely true. And you can see, if you look at the left-hand image, you can see what the near surface layers of this alloy look like. And you can see the difference between the near surface layers and the underlying microstructure. And you can see that the surface is characterized by, in this case, a fairly uniform layer of ultrafine, about 100 nanometer diameter grains. And you can see when we anneal, we get more oxidation, but the grains are stable because they're pinned by the oxides at the grain boundaries. You can see there's more oxidation on the surface. But these materials aren't created by the high temperature annealing process, they're created by the low temperature deformation process during rolling, but they're stable at high temperature. And this we were able to report at the first Aluminium Surface Science and Technology conference that was held in Manchester. And these Aluminium Surface Science and Technology conferences, which were initiated by George Thompson and Herman Terrin, have played an absolutely key role in our continued understanding of these phenomena as we presented more and more work. But these conferences, one of which will be occurring very soon in Stockholm, are absolutely the core part of understanding, the world's understanding of aluminium surface science and technology. And the content of these meetings is really superb. And the leading contributor to these conferences every time comes from Manchester Corrosion Group. Quickly after looking at rolled aluminium surfaces, we looked at a 6000 series surface, and we looked at what happened when it was mechanically ground. And you can see that whatever grit size you use for mechanically grinding, you actually get pretty well the same result. The coarser the grit, the deeper the deformed surface layer, but generally the grain structure, the ultrafine grains, and these formed by grinding are probably nicer than the ones formed by rolling because they have less oxide with them, and you can really see the beauty of the ultrafine grains. And all of these have a profound effect on the performance of the materials. And if you rectify an aluminium surface before painting, you're not going to have very good corrosion resistance because under the paint film you're going to have a very reactive surface. As Stuart was saying, filiform corrosion can be quite beautiful, but lots of people don't like seeing filiform under paint, particularly on things like nicely lacquered wheels or nicely coated aeroplanes or nicely coated cars. And so it was in the early 2000s, it was a huge problem for the use of aluminium in architectural applications across Northern Europe. So there was a lot of concern about looking into this problem, and I actually looked after a European project to really try to understand what was going on. What we were able to show was that it was very much controlled by the presence of deformed surface layers. You can see how quickly Filiform can grow on a suitable surface. There's no cleaning or pre-treatment. These are just ground surfaces that have been, or rolled surfaces that have just been lacquered and then scribed and then exposed to a saline-containing environment. And you can see how quickly, depending on the annealing condition, the filiform corrosion filaments develop. Of course, this is not nice if you're worrying about filiform resistance to a painted surface. And it was very simple to explain what was going on, because within the deformed surface layer, because there's so much stored energy in these systems and in such a fine grain size and such good high rates of diffusion, particularly along the grain boundaries, you can actually get a lot of things going on in these layers that don't happen in the bulk. And really what happens during the annealing process is you're actually precipitating high quantities of manganese-rich dispersoids, and these provide the cathodic sites to accelerate the corrosion reaction and to promote the filiform corrosion. And this is where we were doing some clever stuff, where we were using ion etching to expose the surface and looking at sequential observation in a fairly high resolution scanning electron microscope to see what was going on. These techniques have become much more sophisticated since 2003, but they really show the value of the progressive etching through surfaces and sequential examination in various microscopes. And so it became very clear that if you wanted to control filiform corrosion in 3000 series aluminium products, one of the easiest things you could do is to drop the manganese content, or alternatively clean off the deformed surface layers. Both work really well. If you drop the manganese level from 1% to 0.5% of manganese, or even very low manganese in a 5000 series alloy, you can pretty well eliminate filiform corrosion. And you can see, even with high manganese, if you clean properly and get the deformed layer away, yet again you can't promote filiform corrosion on these surfaces. This work pretty well saved the aluminium architectural sheet market in North America once the ramifications of these understandings were put into practice. On automotive sheet, the problem is very similar. On the 6000 series alloys that are used for car outer body panels, we convinced Jaguar Land Rover, based on some of our early understanding of Filiform, that they could happily use 6000 series alloys without modifying the cleaning and pre-treatment methods used for steel surfaces. And so things were going fine until the Jaguar put the XJ vehicles on the market in 2003, and very quickly some of them started to suffer from filiform corrosion. So I was sent a car door, which is from one of these lovely cars that have been exposed to the environment in Hull, not particularly best or particularly worst environment on the planet, but when we were able to look at that surface, we could see where the paint had been damaged by a stone chip, where the red arrow is. We could see the aluminium hydroxide corrosion product when we stripped the paint off in a nasty organic solvent. And you could see that when we looked at the surface, you can see that the surface of the aluminium sheet was not the rolled surface that we provided to Jaguar Land Rover to make the cars, but it was something that they'd added before they actually did the painting, which was a rectification process involving grinding the surface. When you look at the SEM image on the right, you can see all the marks from the grinding that had been done before painting. And the obvious remedy for this was to stop doing the grinding before painting. And once that stopped, we don't see filiform anymore under painted outer panel products on aluminium cars. So it was a worrying time, but simply resolved again by careful work done at Manchester. And we reported that at ASST4 in the wonderful French city of Beaune, where they provide nice alcoholic refreshment. The This also enabled us to see that although the automotive companies still persist in putting zinc phosphate down on aluminium automotive surfaces, there's actually no need for it. It doesn't really go down very well, although most German automotive OEMs still like to have zinc phosphate on their surfaces for some really obscure, bizarre reason. But you can see if you do some careful ultramicrotomy, again, this is probably Chiron doing this, and you can see that the zinc phosphate crystals actually float above the surface of the aluminium sheet, and the actual adhesion is provided by the fluorozirconic or fluorotitanic acid pretreatment that's put on after the phosphating process. So it's really, this is where we discovered that it was the rinse after phosphating that was controlling the properties, not the zinc phosphate itself. About this time, a PhD student in the department, Frederick Roth, also did some really nice work on machined 6111 surfaces, showing beautiful deformed surface layers of ultra fine grains. And he was also able to show that not only do you get preferential manganese precipitation, manganese dispersed precipitation, you also get preferential precipitation of aging precipitates. So he looked after, having had a machine surface for about 8 weeks, he then was able to do some ultramicrotomy and TEM, was able to show rapid development of aging precipitates on these surfaces, and did a very nice microscopy to show what phases these are. These ultra-fine grain structures are really exciting structures, both in terms of composition of microstructure and mechanical properties, and actually led to some really profound developments in improving the bulk mechanical properties of these alloys, which I'm not going to talk about today, but they're still very active projects. This is where I think we probably had Tim Burnett involved for the first time. He did some really nice microscopy while he was still with FEI, working for FEI, but in the department, and you can see just what happens when you take an aluminium 6000 series alloy, in this case 6016 automotive body sheet, and rectify it. You can see the pronounced surface topography produced by the grinding, and you can see the beautiful deformed surface layer sitting above the normal grain structure. And now with higher and improved resolution low KV SCM, you can really begin to see, you don't just need you don't have to see these ultra fine grain structures in the TM anymore. You can actually pick them up in a good SCM, which makes analysis a lot easier. By ASST5 in Leiden, in Holland, we've actually been working more closely with both UMIST and with the University of Sheffield, and we've shifted some of the attention from automotive sheet to can body sheet, which is still probably the biggest sheet product used in the world of aluminium. And working with Mark Rainforth and his team, we were able to get into even more details of these deformed surface layers. And he found on the surface of can body sheet, not only do you have ultrafine grains and oxides, but you can also have carbides, nice pictures of aluminium carbides as circled. And also you get patches of amorphous carbon, and this comes from residual lubricant that's trapped in these layers. So they're pretty complicated and complex things, but quite beautiful to look at under a microscope. And it turned out that understanding deformed surface layers on aluminium can body sheet was absolutely vital in protecting some of the markets for can body sheet across the world. Because if you don't control the deformed surface layer and you don't get it cleaned away properly, you end up with problems called yellow can and galling. And this was almost catastrophic for Novelis in preserving their can body sheet market in Asia until they actually did this work, had this work done at UMIS, and were able to understand it was all to do with deformed surface layers, and they had to make sure that they were either minimised in production or properly cleaned off before the can sheet was sold. This is another one of my bugbears, which is electro-discharge treatment of rolls before the final pass of aluminium automotive sheet. It's done for steel. It absolutely doesn't have to be done for aluminium, but again, the German OEMs like it, so it's still put on. But the work at Manchester was able to show that this is such a detrimental technique for the aluminium surface. You can see the shingle it produces on the surface, which is meant to be a good thing. But you can see the severe damage it does within the deformed surface layer, and actually makes a lot of pre-cracks, which is not a good idea if you want this surface to be have good corrosion resistance. I still haven't managed to persuade people that this should not happen. Then again, by 2015, by ASST7 in Funchal, Tim was doing some really nice direct examination for the first time of these surfaces. Yeah.
Just could you about 2 minutes to go?
Yeah.
Thank you.
And we're almost there. And if only Stuart had been a bit shorter. But the nice thing, it's nothing to do with his size, just the length of his talk. And it just really shows that if you understand these surfaces and you understand that they have important optical properties, you can actually see whether they're there. So we can now monitor these surfaces and monitor cleaning during, and we can actually tell whether cleaning and pre-treatment are successful by looking at the reflectance of surfaces or the colour of surfaces. And this is really quite important. And this is where we are now, and this is what we're talking about in ASST8 in Denmark in 2019, and we'll be talking about it again in Stockholm next month. And we now can understand that how important cleaning is, and how we can control cleaning in practice, and how we can make sure that surfaces painted surfaces won't corrode, and how adhesive bonds will have durability. So deformed surface layers have been ever so critical. I'm not going to go through it all again, what they are and what they do, but they have really been it's been so critical to save and expand the major markets for aluminium architecture and can body sheet, and enabled the rapid expansion of aluminium in structural and cosmetic automotive applications, and has made it possible to control cleaning and pre-treatment processing. The combined value of these findings would turn into many billions of dollars for the aluminium industry. It's protected aluminium and maintained aluminium in some of its absolute major and growing markets across the world. Just to acknowledge that none of this would have been possible without the support of people within UMIS, Corrosion at Manchester, particularly George Thompson and Chiron. Then people who work there with him, and people who work with me as well, Andres Astes and John Hunter, people at Alcan and at Innoval, and lots of people who I've worked with at UMIS, Tim, Jan Wen, Tero, for example, and plus many others. So there we are. I'm pleased that my voice has just about held out, and I'm sorry I couldn't be with you, but thank you for listening.